Welcome to this session. In this session, we are going to define what we call a Skew Hermitian matrix and give some examples. So definition, a square matrix A, whose elements are A, I, J, is called a Skew Hermitian matrix if every I, J element of A is equal to negative conjugate complex of Ji element of A, i.e., we mean Aij is equals to negative conjugate of Ji. So this is the definition of a Skew Hermitian matrix. That a square matrix A is called Skew Hermitian if every I, J element of A is equal to the negative of conjugate complex of the Ji element of A. In other words, Aij equals to negative conjugate of Aj. And then the necessary and sufficient condition for matrix A to be Skew Hermitian is that if you take A power theta is the same as negative A. So that is the sufficient condition for A to be Skew Hermitian. I remember A power theta is simply conjugate of A transpose. This is what we have. Now let's have a discussion on how the elements along the main diagonal of a Skew Hermitian matrix looks like. So consider elements along the principal axis, principal diagonal of A. So where A, we are assuming that A is a Hermitian, a Skew Hermitian matrix. So remember, by definition of A, which is Hermitian, a Skew Hermitian. Now, by definition, they've said that A ij is equals to negative a ji conjugate. So this is the definition of a skew Hermitian matrix. So along principal diagonal, we have I equals to j. Now let ai be a plus bi. So I'm saying ai because the value of j and I are the same. So this implies that conjugate of ai is the same as a minus bi. This by definition. Now, if I call this definition equation 1, and I call this 2, then along the principal diagonal, one means ai equals to negative ai because the value of j, this conjugate, value of j and I are the same, i.e. ai plus ai conjugate is 0. I'll simply take this to the left-hand side. Now let's replace ai and its conjugate as defined in 2. So I'll have a plus bi plus a minus bi. This is the conjugate, this is the ai itself. So this should be 0. Now this will be 2a because we have bi plus minus bi 0. This gives us 0, which tells us that a is equals to 0. I remember in the definition, a is the real part of the complex number, b is the imaginary part of the complex number. So therefore, a I is equals to 0. Hence, all the diagonal, the principal diagonal, elements of a skew Hermitian matrix are either zeros or purely imaginary. So they are purely imaginary is because when you say A11, AII is given by, say, BI, when it's purely imaginary, then the conjugate of AII would be negative BI, so that when you add the two, because the condition is that AII plus AII conjugate must always give us 0. So when you add these two, we have BI plus minus BI gives us 0. So that one works. And also when the real part is 0 from what you have solved here, also that equation is satisfied. So that's why I'm saying it's either zeros or purely imaginary. So examples. So if we have a matrix A given by I2 minus 3I, 4 plus 5I, and then minus 2 plus 3I, then 0, 2I, then minus 4 minus 5I. This is 2I. And then minus 3I. Then this is an example of a skew Hermitian matrix. Or if we have B given by 0 minus 3 plus 4I. Actually, this is plus. And then 3 plus 4I, 0. Remember, the thing is that, so the condition for being skew Hermitian is that all the elements along the main diagonal are either purely imaginary or zeros. Then Aij is equals to negative conjugate of Aj I. So if this element is 2I, then its conjugate is minus 2I. So the element in this position should be negative of this. So that's why this one is plus. So this is 2I. This must be still plus 2I, so negative. And then C, if we have a matrix 0, A minus BI, and then minus A minus BI, and then 0. This is still another skew Hermitian matrix. And then some deductions or some theorems that characteristic roots of a skew Hermitian so this one, Hermitian matrix is either 0 or pure imaginary numbers. That's the first result. And then another result. Now for the case of skew Hermitian matrices that we discussed. So then say number 2. For the case of Hermitian, number 2, the characteristic roots of a Hermitian matrix are all real numbers. So, and then I'll say number 3, the characteristic roots of a real symmetric matrix are all real, and so a real symmetric matrix is Hermitian. So that's result number 3. And lastly, theorem, just say on its own, that 1 a power theta, theta is the same as a. Then number 2, if you have a plus b raised power theta, the same as a power theta plus b power theta. And then number 3, if you have k times a raised power theta, is the same as conjugate of k times a raised power theta. And then number 4, if you have ab power theta, is the same as b theta times a theta. These results can always be proved from definition of a power theta, which is simply the transpose of the conjugate of a matrix. So where a power theta and b power theta are the transposed conjugates of a and b respectively, and a and b are being conformable for multiplication actually addition, because we have another condition for addition. So those can always be proved from the definitions of a power theta and b power theta. So the next session we'll do some examples involving how to rewrite a matrix both in symmetric and both in Hermitian and skew symmetric Hermitian form. Thank you.